Alright, so we're going to start off with a quick warm-up. We're going to graph this system of linear inequalities. If you haven't done so, go ahead and pause it and hook that up. Once you have done it, you should get y is less than -1 minus x, which is got a negative slope. Now here's the thing. Today, make sure you make a lot of points. Today we're going to finding the intersection point of where these lines cross is going to be important. So make a bunch of points so it's easy to see. Now this is going to be a dotted line. Now I'm at a point where I like to shade once so I don't have a big mess. I like to shade once I graph these lines. Now if you need to shade like this one would shade below. If you need to shade as you go, that's totally fine. Just make sure that your final answer is clear without a doubt what you're trying to say. This is going to be dotted 1 through there. Less than is that way. And then y is greater than or equal to -1. -1. Well, this is a solid line. The third one's a solid line. Looking like that. So it's below the blue line. It's to the left of the purple line, and it's above the green line. So your final answer should be the shaded area up in here, going that way. Now this shaded area is unbounded. This goes on forever and ever and ever in that direction, in all of these directions, right? This is an unbounded shaded region. Well, we're going to use this stuff today to talk about what's called linear programming. That should be the name of today's lesson. Linear programming. And what we're going to do is we're going to use systems of inequalities to optimize stuff. Now, optimization is determining the maximum or minimum value of a quantity. Determining the maximum or minimum value of a quantity. Optimization means ideal. We want the ideal scenario for each one. Now, think about in business. Optimization, there's some things you would want to maximize in business, and then there's some things you'd want to minimize in business. One thing you'd want to maximize, of course, would be profits. You'd want to maximize profits. You want to make as much money as you can. And one way to make as much money as you can is to minimize your costs. Right? So you'd want to maximize your profits by minimizing your costs. And that's what this is talking about. Now, in linear programming, an objective function is subject to a system of inequalities called constraints. The graph of the system of inequalities is called the feasible region. I need purple. Feasible region. All right, so just let's throw some vocabs. After first, we're going to give you some steps too. Step 1. Step 1 is graph the constraints. Smith, I don't know what a constraint is yet. That's okay. First thing you're going to do is graph the constraints. All right. Then the next thing that you're going to do, step 2, is determine the coordinates of the vertices. Determine the coordinates of the vertices. I'm going to add a little bit more of the feasible region. Determine the coordinates of the vertices of the feasible region. Then step 3 is you're going to plug plug the vertices into the objective function. Plug the coordinates of the vertices into the objective function. Now, if the feasible region is bounded, then the function will have a maximum and a minimum value. All right? If the feasible region is bounded, it's going to have both maximum and minimum. If the feasible region is unbounded, then the function will only have a maximum or a minimum. It will have either a maximum or a minimum, but not both. It's not going to have both of those. All right? So these are the steps. Let's do one. All right, now if you recall, step one is graph the constraints. So step one here is we're going to graph these here constraints. So go ahead and graph those. X is greater than or equal to 3, or excuse me, less than or equal to 3. And it's solid line. Less than is to the left. So if you need to shade, go ahead, but I'm going to kind of keep track. This next line is going to be y greater than or equal to negative x plus 3. Now remember, make a bunch of points because we're going to need to find the vertices where of these lines of the feasible region. So make a bunch of points so it's easy to determine. Oh, that's where they intersect. Wow, that is the unstraightest line you've ever seen. Then this last one. Get y by itself. 2x plus 9 is greater than or equal to 3y. So I got 2/3 x plus 3 is greater than or equal to y. Like boom, right there. I see I got an intersection point. And our slope is 2/3 up 2, right 3. Ah, there it is. I got an intersection point. Okay, so I graphed all 3 lines. So now we got to find the feasible region or the shaded area to the left of the purple, greater than the green, so it's going to be above the green. It's going to be below the blue. So your shaded area should be this triangle-looking thing right here. Your triangle is the feasible region. That is the shaded area, the feasible region. All right, so step one is done. Step one is done. We did graph the constraints. Now we need to determine the coordinates of the vertices of the feasible region. So we look at this graph. We got 3 vertices to this triangle. And these points occur at 3, 5, 0, 3, and 3, 0. So we're going to write those down. We got the point 3, 5, oops, 3, 5, 0, 3, and 3, 0. Those are the vertices of this thing. Step 2, check. Step 3, we're going to take these vertices and plug them into the objective function. This is the objective function here. So in this case, it would be 2 times 3 plus 4 times 5, which would be 26. 3, 5 gives us the point 26. Here I get the point 2 times 0 plus 4 times 3, 12. And on this one you get 2 times 3 plus 4 times 0, which is 6. So those are our 3 values. Now let me explain this. This purple area, you are allowed to plug any one of these values into the objective function. This is our feasible region. This is the region that we're allowed, that we're interested in. The only thing is, your maximum and your minimum values are only going to occur at the vertices. All right? These vertices are going to maximize this function, and these vertices are going to minimize this function. So, with these vertices, our maximum value, you can see, is 26. So 26 is the maximum value. The minimum value, it's not 12, it is this 6. This 6 is the minimum That's the smallest one that came out of these vertices. Now, you could try and pick any one of these pink points and plug it in here, and it's going to be somewhere between 26 and 6. It's going to be between those numbers. All right, so this is a bounded region, so we have a maximum and a minimum value. Oh, that was step 3, right? Plugged in the vertices into objective function, we found a maximum and minimum. All right, that brings us on to the next example. Go ahead and graph the constraints first. All right, so I'll graph it here. We'll come back together, see if we agree. All right, so I got my lines. We're going to shade. All right, so check this out. I'm above the purple line, or excuse me, to the right of the purple line. I'm going to start again. I'm to the right of the blue line, above the purple line. So I'm up here in this quadrant 1 area. I'm also above the green line and above the orange line. So here's the thing. My shaded area is everything up in here, up to the green line. Then I ride this green line because it's above the green line to the orange line, and it's above the orange line. Then where it hits the purple line, I'm still above the purple. So it's all this. Notice that this little triangle here did not get shaded. And this keeps going on forever and ever out here. So do you suppose this is unbounded or bounded? Yeah, this is unbounded. This goes crazy. All right, so how many vertices does this have? Well, look at the blue line. The blue line comes down, intersects right here at 8, 0. All right, then comes down this way to this intersection point, and it comes down, intersects at the orange and the purple intersect here, and then it goes on forever that way. So there are 3 vertices here. And then it escapes forever and ever. So our 3 vertices, as we said, are the points 0, 8. We've got the point, what is that? The ballerina point, 2, 2. Get it? Ah. All right. And then we got the point 4, 1. 4, 1. Those are our 3 points. So we're going to use our objective function, plug this in, and you should get 24 when 0 and 8, right? 2 times 0, 0, 3 times 8 is 24. Should get 4 plus 6 is 10. On this one, you get 8 plus 3 is 11. Now, the question is this going to give us a maximum value or is this going to give us a minimum value? So here's the thing. You need to also find a 4th point in this particular case. You need to use what's called the test point. The test point. Now I'm going to use the point 10, 10. Even though it's not a vertice, 4th period, I'll see you in about 5 minutes. Even though it's not a vertice, this test points we need to use. When we use this test point 10, 10, we get 20 plus 30, we get 50. So here's the thing. As this keeps going on forever and ever and ever, think about the point 100 and 100. We would get 500. So does that mean does this feasible region, does this have a maximum or does it have a minimum? because the test point is 50, which is higher than all of these, that means that one of these is going to be our minimum. So our minimum is going to be 10. And because no matter if we put in 1,000, we would get 5,000. There is no maximum value, so this is none. All right. So because this is unbounded, it only has a maximum or a minimum. All right. So this word problem, if you want to take a crack at it, go for it. Otherwise, we'll talk about that in class on Monday or later. Smith out!